Welcome back. Welcome back. Welcome back. Susum Electronics. We're working on the AC DC switch mode power supply. Back with another episode. And I'm excited. We are finished with the schematic. We still have some footprints to select for some components that we missed or that we just haven't done yet. Other than that, we're well on our way for this design. So I'm thinking we're gonna do a little bit quick selection of footprints for the components that we missed. And we might have to look through our notes a little bit to size them accordingly, select, voltage ratings, yada yada packages depending on voltage, etc, etc. So let's see if we can do that. And welcome back to Develop the Potential, where we do electronics from concept to production. I'll show my design. And we got most of the components ready. So all of these are the new ones. So second revision type stuff, but we're putting them all together. So this is still first revision of the PCB. Here you see the rest of the components in various packages, and yeah, nice. Where is this from? I wonder. Right, this must be the VCC component. Yeah, so that's all of the component, and we're still missing this. This capacitor, resistor, and this capacitor. And this one we'll actually start with, because this is a Y type? No, Y capacitor. Safety rated Y capacitor, which we're not gonna or which couples the AC connection between the two grounds. So ground 1, or the primary ground. Can I rename this primary ground? Maybe I can even P ground, maybe I can, no, power ground. Protective, clean, earth. Yeah, anyways, we have ground, and then we have ground 2. So this is the primary ground, and this is the secondary ground. So in DC they're still isolated, but we have, from the primary side over to the secondary side, there can be transferred common mode noise, as far as I understood it. Common mode noise over on the secondary side, which is not good in terms of, people will hook up to this. Here it's 12 volt, but yeah, people can hook up their appliances to this, and it should, I think it has to do with some standards, EMI standards, which we won't get into right now, but as a topic for another discussion. So it's basically to, in case of high frequency noise, to filter it back, to give it a return path to the primary side. So that's the function of this capacitor. And it's a safety rated capacitor, so it's just not any capacitor, but it's a Y type capacitor. And as far as I'm told and understand, 1 nanofarad is a typical value, but I guess you can, you know, change that a little bit accordingly. But it has a lot to do with EMI performance, of course. Bigger the C, better high frequency noise reduction. But bigger the C, we have more leakage current into the secondary side, which is probably not a good thing then. Hooking up your appliances to it, having some leakage. Yeah, so 1 nanofarad is a good in between, where you get good performance for noise reduction, but also low enough leakage current for it to have any impact on the devices hooked up to this. So, and I haven't checked that, but I could go to something like Mouser and maybe type in safety capacitors, and it would come up. Safety capacitors, and then you can select the safety regions, and we want a Y type, and I think Y1, Y2, it's like the classes. So Y2, for example, it doesn't go up to the higher, 350 VIC is the highest. And in this case, at least, Y1, a higher class, goes up to 500 VIC. And termination style. Guess if we want surface mount. But let's check a Y1 and a 500 VIC. And this could, as far as I'm told or understand, it could be based on application, right? If you what you need for a given application. So maybe in some cases we can do with Y2. I will Google it actually, Y type capacitor classes. Y1, which is rated AC voltage up to 500 VIC, and it's a peak test voltage of 8 kilovolt. And it's double or reinforced insulation type. So Y1 is designed for the highest level of safety and in isolation, with a peak test voltage of 8 kilovolt and an AC rating up to 500 VIC. Y2 is a common choice for 250 VIC applications with a 5 kilovolt peak test voltage. And we have up to 265. So I'm guessing that And here we have capacitances, 1000 pico. This is a Y1 now. So yeah, this is important. And it's cool to see the use of this. And I'm curious on the placement on the PCB. I'm guessing it's good to have it as close as possible after the rectification maybe, or before. Do you have it before rectification? So you would basically have capacitor from here to, or from here, or yeah, from here to ground 2. So on the PCB as close as possible to these, because then you would maybe filter it out immediately, but I don't know. So it's a Y cap between the hot ground and the cold ground. Hot and cold. Do, 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 do. um, do, 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 do. So that's a Y1. Then we can look at a Y2. Surface mount, maybe. Da-na-na-na. A lot in stock. Not like crazy amount, I guess. For example, this one, safety capacitor 300 VIC, Y2 rated 1500 VDC. Oh yeah, we forgot to choose this one. To select from. This one is a little bit cheaper. Oh. I'm not sure if you can choose this compared to the other, for worldwide use as an electromagnetic interference suppressor in all Y2 applications, line to Earth. But yeah, I really don't want to speculate too much on this, so I think it's better for the time being to choose something like this. Maybe this is a bit high. Let's go back and check. So we change the safety rating. Just take this away. So we do Y2. No, sorry, Y1. We do Y1. And then we do 1 nanofarad. Um, 250. So either 250 or 240. Let's just check 240 or 440. Target standard, class 2, class 1. Maybe it's a little bit more intricate than just let's check this one out. Y1 440. We got one to choose from. Let's do it's too much, or 440. Safety capacitor. Oh wait, safety. Why? Safety rated capacitor. Right, let's go back again here. See if we can find a different alternative. $400, $300. Y1. Nah, these are the only ones. So what this means, no wait, it doesn't really mean anything. We can still do the 440, which is this one. It's a bit overkill when it comes to voltage rating, but we have the capacitance that we want. So I will copy that and write data sheet there. Good question. What is the wait? So we have LED spacing. Footprint. Chemet. And this one, and then this is the one we get. So manufacturing part number is this one. And then is Chemet. What else do we want to know from this? Voltage rating AC. Or 40 AC. And then the footprint. Safety capacitor. So radial. Lead spacing width 5.5. I guess one of these would fit, though. Where do we have it? This one. So length is 18. Length 18. Length 18. Width is T 5.5. So 18, 5.5, maybe 6 then. And then P, what is P? It's the lead spacing, so P is S then, which is 15. Ah, so maybe this will work. Let's at least start there and then check here again. Length 18, it's a rectangular box. No, I mean that's the only one that would work, I think. Yeah. So then we have that selected. Then I think it was this one, which is an optional. Yeah, we can look into what voltage do we see here. V in. This was like 2 something. So I don't know, capacitor, SMD, 0603 maybe. because we don't see anything else than that. So and I should start documenting. I still have this, and then of course my other documentation, vin pin, which is this one. Yeah, 2.9. Or 2.7. No, wait, 2.9 now. Or it can be. The worst case would be like 2.9 or something. But first we document this. Maybe I should do like that. So capacitor, and this one was annotated as C8. C8, we selected 1 nanofarad. Max voltage was 440 VIC. Max current package. Yeah, correct. Box. Is a bit different. We don't really need to specify the box, maybe, or the package, but nevertheless, we still, yeah, we can even put in the part number and stuff, but we can go over and do that later. Function, filter noise from the secondary. We should write filter high frequency noise from secondary to back to primary side. So or 40 is overkill, but it is Y1 rated. I can really even decide if it's, oh no, it's probably overkill, but it's all right. Because as far as I know, the AC mains can't get higher than that. It shouldn't be higher than that. I guess some fuses will blow before that, I'm sure. Some fuse to protect cabling in your house or in the walls before it reaches us. Anyways, documented. Come on now. It's not the best, and I just named it electrical bill of materials because maybe it will be that in the future, but So do like that to make it a little bit nicer. Maybe a light blue to calm the nerves. Feedback. Feedback loop. I'll do like this. Function area. So where is it? Function area, safety rated capacitor. EMI and leakage. Lack of a better function area name. But this capacitor is part of the EMI leakage reduction, I guess. Maintenance. EMI and leakage maintenance. Maintenance. Is that correct? Maintenance. And all of these are part of the feedback loop, so we could actually do like this, and then we can later on filter by function area, component, annotation, values, etc., part numbers, or even manufacturers to see. Okay, on to the next one. We did this one quite quickly, but this is the C1. And this is on, so let's do C1. I'll put over here too, so it's also a capacitor, 100 nano. And let's do 25. Or max voltage load, so what is the maximum voltage it can see? So it was something like 3 volt or something, right? So the package then anyways 25 volt, so we have the voltage rating. Okay, and the packaging, I'm not gonna get into all like it DC biasing and stuff. For this, I'm just gonna select all the components, make sure everything has a footprint, and of course I'll go over that in the future. But I haven't selected a component, so I'm not gonna fill it out yet. What does this do? This was per recommendation from the data sheet to add capacitor to reduce voltage ripple on input pin. I can take that comment away, and then I rather have the comments here. Yeah, I can actually add that here because that's wait. Have it here. Reduce. So its function is to reduce voltage ripple on the pin of the controller. I'll just write a recommendation from the datasheet. Yeah, right. not capacitor, but it's a Y rated capacitor. Y1 rated. I think this is a very controller pins, or I would just write controller. And then we specify later which pin, of course, on the function. On the function itself. Okay, let's select the next one. So here we select 0603. It would be interesting for future revision to look over and check where can we, go for 0402 packages instead. Here we select bigger packages, of course, of these ones, since they see higher voltages, will have higher power dissipation and stuff. I don't know. I think most is, or the lowest is actually 0603, I think. So we can just stick with that. Like maybe even these ones can be pushed further down, and even this one, perhaps. But it depends a little bit on voltage rating, I guess. This, for example, it says 0603, it's also 100 nanofarad. Would make sense to just take the same one, right? For example. Okay, so that was that one, then this one. So what's the highest we see on the zero crossing pin? I would have to look through the notes again. And then I also need to change these to headings, rather. Zero crossing combines the function of startup, zero crossing protection, and output over voltage protection. We will select an output over voltage protection, 13.2. Right. Selecting capacitor. $92 picofarad. That's that one. Oh yeah, right. This I remember. So this filter here is basically creating the time delay that we need in order for this MOSFET to switch on at the valley. The valley, what is it called? The valley. That's awesome to read it. The voltage valley. We want to achieve a switch on the voltage valley. So we introduce a time delay. Oh, that's cool. I like that. So it doesn't really tell us. Well, it's 16 here. Right. 16. And then here it can also be minus I'd say 50 volt. 0603 also then. Perhaps. But for real, I need to go over them and check. But let's go for a 0603 now. Smoothing of the signal. This is also a recommendation from the datasheet, but let's go back to this one. And this is the beauty of taking notes, document your work. C5 is capacitor. 100 picofarad. The worst case, I should write here, worst case voltage cross, just so we here too, max current, or worst case current. I'll do worst case voltage, worst case current, then we get the power dissipation. So the worst case we get here is 16 volt. Maybe. Anyways, we probably do 50 volt and 0603. This is where I can also cheat a little bit and look at the reference schematics, but it doesn't change the fact that we need to understand why we select the different ones. So circuit diagram. So on the zero crossing, these are 50 volt that they have here. .33 picofarad, 50. Like I said, depends a bit on the function when it comes to capacitors. If it is to, you know, if it's a RC filter, which in this case it really is, right? In this case, this is a RC filter where we want to introduce a time delay. So we don't really care about filtering of this signal, I guess. So if it's higher frequency, we don't care about cutoff being where it needs to be. Yeah, I'm just talking. But yeah, let's take that as a take that into consideration in the future too, that selecting capacitors is much more about, or much more than just voltage ratings. Can be DC bias in order to have the appropriate capacitance and stuff. Which I guess maybe indirectly it also impacts the time delay. That's interesting. And this is why we dig deep into this to understand. So in order to have this time delay, we need 92 picofarads. But if we look at frequency response, is it really 92 picofarads then? Because of DC biasing? I don't know. This, I really like this song. Okay, but just documentation. So C5, worst case is it sees 16 volts, which I think is a fair assumption, maybe. And also looking at the reference schematics, it helps us, but we shouldn't rely on that, so. I haven't written down anywhere else. Oh wait, maybe up at the other pin. Hold on. No, not the V. Yeah, VCC pin. At the VCC pin, but because the capacitor sees the same, or not the same voltage, but it's also connected to that auxiliary winding. So maybe we can, yeah, 16 volt minus 10. Yeah, we also added a note. We added a 100 nanofarad capacitor as per recommendation from the design guide from Infineon. That's this one. So that will go into our Excel sheet too, as an explanation to why we selected that component. So 16 volt is the worst case voltage. Like I said, tells only not even half the story probably. And I will just copy this. Now I can't remember exactly the big difference between this one and this one, but this the dielectric type, could be this. Could be something. Or this something that I forgot. Okay. I'll write in here. Part of the RC filter that is used to introduce the time delay for the MOSFET to be switched on at a voltage value. Could do C4 too, which was 100 nano, and here also the worst case on this is 16 volt. So we selected this one, which we did here, C4. And then I add another note. We added it per recommendation from the datasheet. And the function of it, I'm not sure if we... At least we know the other VCC capacitor is used to store energy. Enough energy to secure that VCC voltage will never fall below the under voltage protection threshold. But I guess we can assume where was I? Here? No. Momentary drop in voltage maybe? Or just decoupling? Decoupling capacitor? Question mark. We'll look into this. Okay, let's move ahead. I'm not going to document all of them. I don't have to do it in exact same order. Let's just C7. C7. And this one. At the in VCC pin. This one was 1 nanofarad. This was also per recommendation from the data sheet, I think. Smoothing of the signal of the CS input signal. No. Feedback. To the controller. And then we check our notes again. Look at the CS pin. CS pin. Current sense. Purpose of this pin is to accurately switch off, is for accurate switch off determination. So VC, oh wait. Yeah, it is on the CS pin. Alright, then I wrote wrong in this file. See, so smoothing of the CS input signal to the controller. Yes. A recommendation from the data sheet. Have I connected it wrong here? Or? Right, this might have I might have done that one wrong. This should be the feedback pin, sure. Should be the feedback. I remember now. Yesterday I did an update to the footprint or the so that's now it's correct. So feedback pin we need to look at actually. Now I am confused. No, right. We are correct. We are correct. VCC pin. Feedback pin right here. Is to determine maximum CS voltage equivalent to the transformer peak current, and it determines this zero crossing counter value according to load conditions. We add per recommendation of the datasheet. Between feedback pin and ground to smooth the signal. Doesn't really say what voltage it is here on the feedback, but we can look in the datasheet. So here, pin layout, okay, it's feedback. Doesn't say really. Feedback. While the feedback signal VFB yeah. So VDD from VCC, no, where's VCC? Thank you for the like. Whoever liked, give me a like. Appreciate it. I appreciate it. So again, we're not going to speculate so much. We're just going to see what's the worst case voltage here. We take it from there. Feedback max 2.75. Max feedback current. Ref. Yeah. So it doesn't seem like it will be any bigger than 2.75 volt, I think it said. Go back. Yeah. 2.75. But if it's always that, I'm not sure. Right, here we select level 2, level 1 or level 2. I think it's safe to assume. So this is also 1 nanofarad, and we also use that there. Nowhere else, maybe. Either way, I think it's safe to say we do this one as well, 0603, and then probably like 25 volt or something is fine. C7, and we can take away this comment that it smooths the signal. And then this one. Should we bother? Do we have to? Is the question, rather. Burst mode entry level can be selected by changing the different resistor at a cell at the feedback pin. There are 2 levels to be selected with different resistors, which are targeted for lower range ABM power level 1 and higher range ABM power level 2. So you select either open or a value of 580 kilo ohm to 670 kilo ohm. Look at the reference schematics. They just have it as an optional component just for, oh no, I don't know if they have it at the layout. Here I don't want to cheat too much, I don't want to look at the layout. I want to do that myself, and then I can rather check if I've done a good enough job. Damn, it feels good to have gone through the whole transfer function part, because that was tough. That was, and I won't say that I completely got it, you know, under lock. That I will do when I've actually simulated this part in Simulink or LTSpice or something. I want to figure out how to do that in order to verify everything here. This and the output coupler and the power output, the output stage or the power stage also. Okay, where were we? We selected this one. This one. That's just for now. That's just for the sake of... Wait, look at the data sheet again here. $180, 670. Mm-hmm. Don't really know. Yeah, like I don't really know the function, this ABM. So ABM at light load. Okay, so it's at light load conditions. The IC enters ABM operation to minimize power consumptions. Details about ABM operation can explained in the following paragraphs. The burst mode entry can be selected by changing different resistor, which we know there are 2 levels to be selected, which are targeted for the lower range of ABM, level 1, and a higher range of ABM power, level 2. The following table shows the control logic for the entry and the exit level with the feedback voltage. I don't know enough about this to really make a decision that we will stick with. So maybe rather for now we leave this completely out. So that's the only one that we leave out. Or 13. I can document that. It has to do with the ABM operation. So R13. Controller. Maybe I write like this, controller. Oh, no, doesn't really matter. Controller. So it's unknown. And yeah, I guess the worst case here would be the same as this one, which I think we wrote was 2.75. 2.75. C7. Same package. Smoothing of the feedback input signal, and then this one used to determine ABM operation levels 1 or 2. Or is it optional? Question mark. I mean, I guess so, since one of them were open and the other one was a fixed value. That's all I know. So I'll leave that open. Like, not open in that sense, just not, I haven't decided on this one. So we leave that completely undecided. We'll leave it undecided in terms of package. I think this is the only one that we haven't selected. So here we can say calculator. Worst case voltage here is 16 volts. Think. And divided by 27 is 0.59. milliampere. right? Yeah, or actually, I do 16 squared divided by 27, which is 9.4 milliwatts. So resistor R11, R11, worst case 16. Oh no, wait, no, 27K, worst case 16 volt. What did I say? 9.48 milliwatts. Can maybe fix this. It's possible. Ah, perfect. So value. $16 divided by 27, 0.59 milliampere. Also controller, and then this R11 then. A part of the RC filter. And here I would just write in which C it is, C5, C5, C5. And this then C, or no, R11. Cool. Then we can update as well. Cannot add R11, R13. R11. Oh, I didn't select the footprint. Sorry. Sorry about that. So, if it's 9 milliwatt, that is the max we can get away with. So, resistor 0603. We do that one, 0603. And then find a power rating or power dissipation. .1 watt then. Yeah. So now we still have one footprint that we're missing. Yeah. No net found for symbol D4 pin 3. Perfect. One step closer. Yeah, we have this safety capacitor, Y-rated capacitor. Huh. It's quite big. Just guessing like before, guessing where it should be. So if this is the output, or this is the output stage, right? You have the diode, the output capacitor, and then the load. And you have noise coming in from the primary side, which this is the primary side. You have noise coming in on the secondary side from the primary. You use the safety rated capacitor to filter out EMI from secondary back to primary. So we provide a high frequency AC coupling. Yeah, it makes sense that we do it before the rectifier then. Yeah, I would say so. Now for PCB design. I think we should start with that again, or continue with that. So we still need to document in the bill of materials. Have we done as much as we need to do right now, so we can wait with that. It's also a little bit of a tedious job as well, even though it's very necessary. I think it's actually really nice to have it like this, and especially to have those small comments, why or what's the function. I feel like I'm I feel like I'm repeating myself, but that's the whole part of doing electronics from concept to production, is repeat yourself, understand what you're doing so that you can do designs like this on your own and really understand, find good processes and ways of working. And I like this to have a boom. So maybe it's simplistic, maybe you could have this integrated into the software you're working on, if you're working on Altium Designer or something. I love that I'm getting some viewers, so thank you for watching. Really appreciate it. It's fun to talk electronics with you, even if it's just me talking in my head. Feel free to drop a comment if you want. Yeah, I don't see anything stopping us. I just want to write here, add EMI filter at input, question mark. That's another thing to do for a third revision. Adding an EMI filter here. I guess here, or if you add it here. Whoops, I did not mean to press Steam. So I need to close that. We don't want any distractions here. think it's safe. So yeah, either here or here. But I have documented a little bit before. So an AC/DC switch mode power supply, we have the input 80 to 265 VIC, so AC voltage. So this is a universal input that we're making, a power supply input. So we have filtering first, which is optional written here. So, and I'm not sure if it is or if it's. I guess you should check that. Like when you're working on it professionally, I mean, you would check that and you would add filter where it's applicable. You wouldn't just add filtering. That's why it's optional, maybe. At least that's how I've drawn it. And then rectification and active power factor correction, which is so in theory optional, maybe. But I guess we're kind of doing that with our controller. I'm not sure. Not gonna get into that now. But anyways, I have the filtering before the rectification. So you would have an input stage that would be noisy, and then you have a filter. Starting to feel like it's not optional and that you should have an EMI filter in the beginning. But I want to create one. So for the sake of this project, I will add one. So it's on my to-do. But I think for now we're good. We're good. We have everything here. We have the feedback network. We have all components selected. Every one got a footprint except for this optional component. Even this we have, which is this big thing, which should probably be located somewhere here. I'm guessing. Okay. Wait a minute. What is this? This with, oh yeah. J1 and J2. But why do we have a third one? We don't need a third one anymore. J2, J2. Yeah. J1, J2. J3. What is? And looking at our, we have 4-layer board. Layer 1 stop, layer 2 is power ground. P ground 2. And then bot. I feel like I should start documenting. So I'll go further down in our documentations. Then I'll make a new chapter. PCB layouts. Stack up. stack up. In the following chapter, we will do the design of the switch mount power supply. I don't really have to say so much more than that, but I will, of course. Later. So stack up, we need to look into just maybe we should start with making some assumptions or questions for ourselves, how things should be located on the board. Can I move around components? I guess not. That's nice in Altium Designer where you can move things around in 3D view. Damn, I'm really not a fan of this package here. And if in the future we'll also look into this transformer here if we select a different one, a better one. But yeah, at least we have an input. We have an input to a bridge rectifier. We have the C in, and then from the C in, oh wait, V plus, on the V plus, I need to put up the schematic. I'm just gonna start with placing things a little bit around according to where I think they should go. So for example, these three, which, so we have R1, R2, R3. And maybe I can take away a bit. Silk screen, courtyard. So it's a bit easier on the eyes. Objects. Let's user drawings. Fab layer maybe. So or I guess maybe the courtyard could be good to have. If I go, yeah, because then I see I can't go past that point, moving the components. I can't, for instance, have it here. That would not be good. So something like this, they're all in series. Now, question here is, what is better in terms of layout? You know? that's something I always find a little bit tricky with layout. Like I try to think logically or just systematically, like in a like like in a schematic where you see how things are logically connected, but on a PCB layout is physical. And everything has a physical implication. So what are we doing here? We're sensing the voltage. Right. To this pin. There's nothing complex about that, I guess. It's just I need to update with some nets here. Can't be doing this design like this. It's not clean enough. Let's go over and do that. Just at least to have R1 to R2. What am I doing here? Come on now. Wait. How do I get it at the other side? Oh. R2, R3. 2R3. 0.5. Come on now. So better. So that's that one. Here we don't have anything. ECC. D1. Cathode. Maybe I call this D2 anode instead. R6, R6, R7. .5. Oops. R7, R8. Probably not the best net naming in the world, but I think that's all right. I'm just trying to be thorough, you know, and yeah, have a good way of working. MOS gate. MOS source. Maybe fett. MOSFET gate, MOSFET source. Feedback, CS. Why do I keep pressing that? Yes. Okay, it's actually, I need to end the stream in a moment here. Something is wrong with the grid here. No, something is wrong with the grid. I'm not gonna, wait. Put it there. CS, and then we have feedback here. And then we have a bunch. No, we don't actually. We have everything nicely net labeled. Except for these two. So I will do here, last one. R10. And then make that 0.5. Huh? What is going on here, mate? Okay, so there you go. And then we do update. Oh, now everything has net name too. So it's a bit cleaner to see. So we see where everything goes. Is it better to just have it like this, I wonder? And then you have this into this pin, something like that. Let's check. I've been streaming for 1 hour 46. So I think it's soon time to go. But I appreciate you watching. So if you want to see more of the stream in the future, feel free to subscribe And also put a like on the stream if you feel like it. If this content is interesting to you, be my guest. It's awesome to have you here. We're gonna do a lot more design than just this as well. Lots of cool ideas for some designs after this. So right now I'm focusing a lot on power electronics. We'll also go into different fields. Automotive, for instance. Even medical, lots of high frequency audio and stuff. I want to work with that, so lots of cool things. Cool. Okay. But yeah, I will end the stream for today. I thank you so much for watching. Appreciate having you here. Feel free to like the stream, hit that subscribe button. And I'll see you for another day of designing electronics from concept to production. Appreciate you. And until next time, ciao.